Hi, kids. Let's do some reparametrization. That sounds devastating, doesn't it? Of course, it would be awesome if I had my pen. Oh, there it is. All right, so length of a curve is given by this formula. I kind of hinted at that in my previous video. Then this should not be surprising to you, right? This really just is Pythagoras, right? The integral of the magnitude, right, of the tangent vector. So if I ask you to determine the length of a curve on the interval 0 to 2 pi of this function, it's kind of sort of like, I don't know exactly what this looks like, but think about some space curve somewhere, right? And if you could, like that was a piece of string, right? And if you could pick it up and straighten it out and measure it, how long would it be? Now, this is a math class. Mr. Getz always makes fun of us because we don't do anything with units. So it's just undetermined units. I don't know, fathoms, furlongs, um, um minutes per, I don't know. I'm just making stuff up at this point. So you get it. Anyway, determine the length of the curve. So at this point, I am just going to plug and chug into a formula, right? So the nice thing though, I want you to watch a little bit of this algebra. So certainly I need r prime of t. Chain rule. Now, I want you to look at what happens here. Thank you very much, trig identity, right? I'm going to factor the 36 out of there. And what do you have right here? Right? Cosine squared of anything plus sine squared of anything is what? That's all just 1. So I have 36 times 1. That's sweet. Look for that. And I don't care if you write 2 root 10 or square root of 40. It doesn't matter. But notice I wanted you to do this on the interval 0 to 2 pi. So what have I gotten here? I have just got this expression. This is all I've done now. I have to take this and integrate. So now the integral of 2 root 10 from 0 to 2 pi, that's just a constant, right? So it's 2 root 10t minus 0, right? Arc length of traveling along this curve from time 0 to 2 pi. Okay, yay. Feel pretty good about myself. Now, the integration that I had to do with this one was pretty nice, right? Firstly, I had a really nice trig identity here that simplified my expression that I had to end up integrating. So I was integrating just a constant and got t, right? The algebra was nice and the integration was nice. Number 3 and number 5 of your homework are devastating. Don't feel bad about, right? I put Slater up for a reason. You are at the point now sometimes where you do need to watch and look at how the problem was done. You should then try to do it yourself, right? If you copy, a good way to do problem sets at this stage of your math career is to, if you need a lot of help with them, whether it's from someone else or from some website, that's great. Do the problems, put them aside at some point, and then see if you can redo them on your own as if you were in a test situation, right? These problems are challenging. The algebra is challenging, right? The algebra and the calculus pieces, much less the concepts. Oh my goodness. All right, I've done enough scaring you. All right, now I want to talk about a curve C given by some vector function and its derivative. And as long as I travel that curve C once, I'm going to, from time A to time B, I want to create an arc length function. Now, I do want to remind you about something up here. If I have a curve C defined by a vector function, I can often represent that function multiple ways. For instance, let's pretend I had some function r of 1, and I called it t squared, and t cubed. And I said that was from t is 1 to 2. Well, I could make some other function. I didn't do very good on my space planning here. I could define another one. And define u to go between 0 and ln2. And trust me, and if you don't believe me, go ahead and graph it. You're going to get the same freaking curve, right? So these are two different parametrizations of the same curve. A curve C can have multiple parametrizations. That's a mouthful. Right? This has the parameter t. This one had the parameter u, but it was the same space curve. So hold that thought while I define an arc length function. In that previous example, I just found the arc length, right, from 0 to 2 pi. So what if I want to make an arc length function? So S means arc length. Is the integral from some starting value as t varies of the magnitude of the tangent vector, which looks like this. Hey. So that's an arc length function, right? So I'm just going to be able, if you look at that previous example where I ended up with, right, plugging in, right, I basically did a definite integral. What if I differentiated both sides? And this should remind you of first single variable calculus, right? What if you differentiated both sides? Take the derivative of an antiderivative. What happens? I took the derivative of s, which means I took the derivative of an antiderivative, and I just rewrote it again, the derivative of an antiderivative. But remember what you had to do. It's going to undo one another, and then you're going to replace. Notice I had to have my dummy variable. Remember that? Dummy variables. So now I have wait, what does this say? The rate of change of the arc length function is what? Right? I mean, what? Can you think about what that's saying? Right? The derivative of your arc length function is just, right? It means you're kind of moving along in units, right? Crazy. Right? It is the magnitude. Whoa. All right. Determine the arc length function. So make sure you highlight this word when you're in an assessment. Am I asking for the arc length or am I asking for an arc length function? And then I'm going to ask you to reparametrize with respect to arc length. What does that even mean? All right. Here is our R of t. Firstly, the starting point, right? The starting point is t is equal to 0. Right, because they told us, right? Remember in that, I'm going back to the same problem where they said from 0 to 2 pi. I just want to not have this ending point. I have the start, but not the end. And I did find r prime of t, and I found that r prime of t was 2 root 10, but I'm going to turn that into a function, and I'm going to integrate from 0, right, the starting point that they gave me. But now notice I replaced the 2t. I don't want to stop. No stopping. And I integrated 2 root 10, and I got 2 root 10 t. Right, because I put in t, and then I put in 0. Now look at what I did here. Notice what's going on. I have, remember this is S. Let me rewrite it this way. S equals 2 root 10 t. I want you to get t by itself with respect to S. So all I did was divide by 2 root 10. This is the reparametrization step. Look at what I've done. Reparametrize. I had a parameter t, but now I wrote t in terms of arc length. Matter of fact, the arc length is divided by what? Right? The magnitude of the tangent vector. So what I'm doing is in here, instead of inserting time, I'm going to be inserting time in terms of arc length. So every place I saw a t, I put s, right? Or I'm sorry, I put t in terms of s. So I had 2 times s over 2 root 10, right? That's what happened there, and the 2's went away. Do you see the same thing happened here? This was 2t, so 2s over 2 root 10, and the 2's canceled out in both of these things. This is the reparametrization of r in terms of arc length. Okay, or with respect to arc length. You've got arc length inside of R. And you might want to say, why, Ms. Getz? Why would we do such a thing? Why? Because now we get position, right? Like if I know, I might well know how far I've gone. So where am I on a curve after I've gone a certain distance? That's what the reparametrization does for me. I thought this was pretty cool, right? How it just drops in all like this. Trying to highlight what the purpose is in going through all of this is as long as I know where I'm starting, right? I went through a bunch of reparametrization, which I can't even say. It's a bunch of nasty algebra, but because what I got out of this was the ability to say, for example, well, let's say I had, right? So let's say I had some ridiculous, and I'm completely making up this graph. I have, right? Let's say I have some curve that looks like that. And let's say at time 0, I'm here. And at time 2 pi, I'm over here. But let's say that I knew the length of this. Let's say I knew the arc length. I want to know this position. What is that position? Well, here's the position vector in terms of arc length. So let's pretend my arc length was 4 pi root 10. So what was my expression? My expression was s over root 10, 3 sine s over root 10, and 3 cosine s over root 10. So in for s, I am going to put 4 pi root 10 and what do I have? So the position after traveling 4 pi root 10 units is 4 pi. Sine of 4 pi is 0. Cosine of 4 pi is 1. There is my position after traveling 4 pi root 10 units. OMG. Check. Let's do another one. Reparametrize this helix with respect to arc length. Right? So what are your keywords here? Which means get rid of this parameter t and change it to arc length. So step 1, there's my initial condition, or my initial position, I'm sorry, at t equals 0. Right, I had to figure out, right, 1, 0, 0. Do you get that? Do you see where I got t equals 0 from? Right, here's t. T is in front of k. They told me k was a 0, so t had to be 0. So that's my starting point. Then I took the derivative. Then I did my algebra, and what do you get here, right? Sine squared plus cosine squared is 1. 1 plus 1 squared is 1, so I got the square root of 2 there. Then I'm going to do my arc length function. So my arc length function dummy variable. Take that expression and get t by itself. Right? This was s. S in terms of t is root 2t. Get t by itself. Now reparametrize. So my original r here is not cosine t anymore. It's cosine of t. Sine t, sine t. Okay. Again, the whole purpose being, this is now the position vector for values of s, which is arc length, along the curve measured from its starting point. Woohoo! Reparametrization. I gotta practice saying that word.